So the idea today is to move forward with the subject that we have already started during last lecture. So just to recap a little bit, we are moving within the subject of the floating frame formulation. So floating as an alternative to the absolute nodal formulation that we have already investigated. The idea of adopting this formulation was, as we have seen, enabling the user to also adopt reduced thickness models and in general non-isoparametric models, elements, sorry, like beam elements or shell elements, which, as we have seen, when used in an absolute nodal formulation would comport, let's say, misrepresentation of the energetic content of a motion. And this would be, a pity not to be able to use such useful elements. And so we introduced this formulation. We saw that this introduction and the consequent adoption of this element came at a cost, the cost of having small deformation-induced rotation. Okay, not small rigid rotations, but small deformation-induced rotation. And the circle that we are going to try to close here is the following. So we start from, let's say, a body. We divide it, we use a restricted formulation, which, as we have seen, is meant to discretize, eventually, the continuum. Once you have discretized the continuum, you choose which kind of physics you want to adopt to represent each element, depending on what you want, how rich you want your model to be. And so you define a number of elemental variables, or of node variables. So a number of nodes, a number of variables that you want to associate to each node, and eventually the shape of each, shape function of each element. Then, from here, you go back, you start going back. So as we will see today, you have to connect the different nodes, different elements. So there is a connectivity issue. Then you have to impose some reference so that rigid motion between local frame and the body will be eliminated. And then eventually you will start to develop the mass and the stiffness matrices of the element. And then from the element, the mass and stiffness matrix of the body. And then we will pass from the body, from the representation in the body frame, to eventually the representation in the inertial frame. And here you will be able to write your dynamics equation. So this is the overall, path that we are going down to. So it's basically from the very start, to the end. So just to continue from where we were at, let's make reference to the picture that we were dealing with last time, which was the following one. So if you remember, our idea here was to basically introduce, we started from the following definition. So we have that the position described with respect to the element frame of the body I, so element J of body I, could be written in terms of some shape elements as a linear combination of the nodal variables. Now, what we actually eventually did was to introduce the intermediate frame. I1, I2, and I3 over hat ij, so that we have two basically main hypotheses. So I1, I2, and I3, sorry, the original element frame and the new intermediate frame are parallel. Then we will see again. And secondly, I1, I2, and I3 as origin in O prime, which is the origin of the body frame. Okay. Body frame B1, B2, and B3. Let's actually, just for the sake of clarity, remove this. Okay. So these were the two hypotheses, and we had this new coordinate frame was called the intermediate frame. Okay, so this is really just a new frame, which really can be called intermediate because it's intermediate between the element frame, the original element frame, and the frame of the body. In this new element frame, we checked that we could actually write and here I just say checked, meaning that we actually controlled it, we verified it, that meaning that if I wanted to describe the position of a point of the element with respect to the new intermediate frame, resorting to the element coordinates, to the, the nodal coordinates described with this new intermediate frame, I could make use of the same shape functions, as long as this intermediate frame had these two characteristics, parallel and the origin eventually. The second, in fact, is not mandatory for this property, but it is actually mandatory for what we want to develop. So eventually, having proved this, we could write the following. So supposing that by definition we had Eij, so the vector of nodal coordinates in the intermediate frame could be written as a matrix C1 Ij of t, function of time, applied over Qeij, where this is the vector of nodal coordinates expressed with respect to the body frame. Okay, very well. This, as we know, was an n times 1 vector. This is an n times 1 vector. This must be an n times n matrix, which basically describes again the mutual orientation existing between what? The intermediate frame and the body frame. Okay. The same exact kind of reasoning was applied not to the vector of nodal coordinates, but just to the vector of position. So this is basically a definition. So you can actually put the 2 points from right to left, and this is a definition. Eventually, we could also write that the position of a point within the element ij described with respect to the body frame could be written as a matrix C2 ij, eventually function of time times x ij. Okay, and therefore, if we expand x over hat, this eventually wrote So again, this is the position vector of a point P whatever within the element with respect to, again, B1, B2, and that's it, and B3. And again, since here we have a position vector in space which typically has a dimension 3 times 1, and this is basically a 3 times 1, this must be maximum dimension 3 times 3. Okay? All right. In fact, this is a 3 times 3, this is a 3 times n, or in space, we saw this, for example, in our case where we had six nodal variables, and in the 2D space, this was a 2 times 6, if you remember, the shape matrix. Okay, the consequence was that we could write the following. This is just a recap of what we were able to achieve last time. So C2 ij, function of time, C ij, not a function of time, of course, C1 ij, function of time, and QE ij. And this is, of course, a function of time. Okay, so you see, through the intermediate coordinate system, we basically were able to relate the nodal coordinates expressed with respect to the body frame to the position with respect to the body frame, meaning that knowing the nodal coordinates expressed with respect to the body frame, we were able to interpolate whatever position of a point within the element with respect to the body frame. So we were able to reconstruct, in this case, the position field. So we know the nodal coordinates, and we are able to reconstruct the position field with respect to the of every point within the element with respect to the body frame. Okay, but again, this can be seen just as a complication somehow. So far, we made here, and this is very important, simplifying hypothesis. Let's say okay, an approximation, simplifying hypothesis, meaning that, in fact, we do not require the intermediate frame to be always parallel to the element frame, but only before deformation. So only initially. So we say that I1, I2, I3 overhead is only initially, meaning before deformation, at deformation 0, meaning that if you have a rigid motion, they continue to be always rigid. What makes parallel? What makes them not parallel anymore is the presence of a deformation. Okay. Initially, so I can say until deformation starts. All initially parallel to I1, I2, and I3. Okay. So to the element frame. This is very important. Why? Because initially, because as we have seen on Monday, this means that our two matrices, C1 and C2, are not function of time anymore. So the direct consequence is that C1 ij and C2 ij are not function of time anymore. Meaning that, I take account of their value, which is given basically by the mutual orientation of the element frame. I choose an element, I see what is the element frame, I compare it with the orientation of the body frame, I estimate C1 and C2 for that element, for that body, and that's it. Okay? Then I don't care about it anymore. All right, so just to rephrase it, we can write it like this. This, of course, stays a function of t. Yes? Mm-hmm. See, so what I'm saying is that basically, so the intermediate frame is just a translation of the element frame. It is placed at the origin of the body frame, and so before deformation starts, there is a certain angle between the two. Okay. Then, if you have a rigid motion, if you leave on the body, you don't just see anything happening. All right. So there is no variation or whatever. Then, when there is a deformation, in theory, actually, of course, what happens is that the element frame follows the deformation. So he justly, acquired a new orientation in space due to deformation. In theory, the element frame should follow this reorientation, and therefore it should vary its orientation with respect to the body frame, which also varies because of the deformation, but typically not in the same way as the element. Okay. Instead, what happens is that the initial, let's say, mutual orientation of the element frame, of the intermediate frame and the body frame stay constant in time, no matter what. Okay, and even if you do this approximation, you still keep on relying on the same element shape functions, and this is an approximation. Okay, which is acceptable as long as this reorientation due to deformation is small. Okay. So in fact, if you really want to be precise, you could write as a function of time. So the function of time is here, but only because it's here. Okay. All right. So this is the cost of basically being able to use these, non-isoparametric elements in the intermediate, the floating fair formulation. Now, we have two additional, let's say, tasks that we have to perform. What are these tasks? Well, typically, a body is discretized into many elements, okay, more than one. And when you have a node which belongs to an element, but also to the neighboring element, what do you do? How do you actually enforce this connection, this connectivity, in fact? This is the first point. The second point is a point that we already know. The deformation process makes non-unique anymore the relationship between a body and its frame. Because eventually there is no more clear separation between the body frame and the body. How the body frame has to follow the deformation of the body is not a matter that is universally defined. It is arbitrarily defined. Since it's arbitrary, you have to enforce the fact that there is no rigid motion anymore between the body frame and the body. And this has to be done here as well. Okay, so we will do it. All right, so we could call this connectivity conditions first. So we could use this picture to clarify a little bit things. Should be this one. Okay, so you see here, the simplest case possible is a body composed of two elements. In this case, we have two 1D beam element with only, in fact, two nodes, and there is not even a rotation. So these are really the simplest possible elements. And you see you have, so the first element here. In fact, you see the subscript here associated to, well, in fact, no. This is, sorry, the first element. I stand mistaken. And in fact, here J is equal to 1. And this is the second element. And in fact, here J is equal to 2. And you have the first node and the second node of each element. When they basically, here you basically consider them separately. But eventually, in a body, they stay attached, unless there is a void. But typically, this is not the case that you have to consider. Usually, you play with continuum mechanics. So you pass from 4 nodes to 3 nodes. You see, 1, 2, 3. Because eventually, these 2 nodes, they coalesce into one. Okay. Well, you have to basically enforce this fact. So if you do consideration, you could write that nodes 2, I1 and 1, I2 coalesce or merge to I. You see, in this case, you basically you lose the information on the element, because here you only have an I. You see, at that point, this is, you see, an information only associated to the overall body. Okay. So J index vanishing. Sometimes this kind of operation, I'm not sure if you're familiar with finite element codes, or Nastran or ANSYS or whatever, you have this condition which you call node merge. What does it mean? It means that when you have different bodies, you don't do it actually for elements, because for elements, of course, it's automatic. But when you have to mesh different bodies, and they have, for example, a face or more than one surface which is in common, I mean, the two meshes eventually, they should coalesce. And typically, the best condition is to have the nodes of the mesh which are just coinciding between the two meshes of the two bodies, okay, along the surface which is in common. But then these two nodes must be considered as one, a common node. So they must coalesce. And typically, there is an instruction to do so in many codes, at least they used to be, which is called node merge, merging of the node. And this is basically what we are saying here. In this case, we are enforcing it between two elements of the same mesh, if you want. But it's actually the same principle when you consider it, two different nodes of two different bodies. It's the same. Okay. So you define the vector of nodal coordinates. So we define Q E I. Please, note the difference between Q E I and Q E I J. So this here is not the same as here. There is a J missing here and here. Because this is the vector of nodal coordinates expressed with respect to the body frame. This is the vector of all nodal coordinates. This is only for the element J. This is for the overall body. So this is the vector of all nodal coordinates of the body I, of all the elements. Okay. What we want to basically do is to introduce a connectivity matrix. So we introduce B, it's typically called B1 IJ, so that Q E IJ, the one that we had before, is basically equal to B1 IJ applied over Q E I. So basically, I get the element, the vector of nodal coordinates for the element J as a down selection of the vector of nodal coordinates of the overall body. So meaning that this, what is it? It's a Boolean transformation made of 1 and zeros. Okay. So again, this is the vector of all nodal coordinates. And this is the vector of nodal coordinates for the j element. This means, as I was saying, that please note that B1 has two indices. One is for the body and one is for the element, meaning that each element has its own connectivity matrix. Okay. It's a Boolean operator, which makes a down selection. So, for our case, we have two elements we saw, no? We have Q, E, I1. If you go and check, it was basically done like so. Sorry, no, this is not a vector, of course. Q, E, I1, I1, and it was the component 1, component 2, component 3, component 4. If you go and check this picture, you see you had QE 1, 2, 3, and 4. Okay. Transposed. And the same for element 2. Meaning, so you have these two vector of nodal coordinates for the two elements, and we add that QEI was in fact QE1, QE2, QE3, QE4, QE5, and QE6. I. So what I'm saying is that you have these 6 coordinates in the overall body, 1, 2, 3, 4, 5, 6. And when you have to pass from here to here, you have to enforce that this is the same. Okay? And you can do it exactly with the connectivity matrices. And you do it like so. QEI1 is equal to what matrix? Well, this is basically I didn't want to confuse you. So if this is, you see, this we call as an n times 1. But this, of course, has a different dimension. We could call it, I don't know, m, if you want, the total number, m. You see here, instead, in fact, in our case, n is 4 and m is 6. So it means that this has to be a what? An n times m matrix, no? And in fact, in our case, this will be a what? Oops. Let's look like this. 4 times 6. No? So, in fact, you have 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, and then the remaining two columns are all 0. Basically, you are just saying that the first 4 elements of this vector are equal to the whole vector of this. And if you look at it, it's correct, no? Because you're saying basically that what? Oh, that this is this, this is this, this is this one, and this one is here. Okay, that's what you're saying. Then, exactly in the same way, enforce the same concept. So you see, it's really just a matter of ones and zeros. And that's why they are called Boolean operators, because it's just 1 and 0. It's just a matter of selection. But when you say this thing, eventually, what is it that you're saying? You're saying that QE for example 3 is equal to QE3I1 okay. Basically, and this eventually means this one, that you're actually, you see, you're imposing an equality. Okay, you're saying that basically by saying, selecting these two different, element coordinates to be equal to the total, what you are imposing is that if you go back and check the image, you are really saying that this is equal to this. No, I am mistaken. Sorry. No. It's one here. Okay. Otherwise, it would not be okay. Okay. And also the same here. So you have Q, E, I think it's 4. And here, if I remember correctly, it's 2. Okay. For the sake of clarity, you can just look at the picture here. You can just reuse it here. You see, you're saying that this one here, this one here, and this one here, they are the same. And actually, let's do it like so. That is clearer. And then you're saying that this, and this, and this, they are the same. Okay, so these are basically you're really enforcing connectivity. Okay. So through B1, I1, and B2, B1, I2, we enforce connectivity, element connectivity. Through basically what actually may appear as just a selection, but you will see that this operation has very important implication. We will see it in a moment. Okay. So this is the first operation that we have to do. Then there is a second one, but before actually going on, you can therefore write the following, just to complete it. We had, if you remember, we just wrote it. This could be written as C2, Ij, C, Ij, C1, Ij, QE, Ij. But now, see? Okay. And this is typically written as N, Ij, QE, I. Okay. And this is again what? The 3 times M. Well, this is M times 1. So eventually, I was able to introduce, this is a constant matrix, meaning that you calculate it once and then you're done for each element. You are eventually able to connect the vector of all nodal coordinates expressed with respect to the body frame to the position of a vector of a point within the element J. Okay. Okay. At this point, again, we have to address another issue, the issue that we mentioned before, meaning that we know that element-shaped matrices are able to encompass rigid motion. We took profit of it, in fact, to introduce the intermediate frame. We saw that if you take into account a rigid motion, in particular translation, you can use the same shape matrices because they are able to describe it correctly. But we don't want it to be done in an uncontrolled way. We want to be sure that when you describe a deformation, you are only describing a deformation. You are not taking. You want to take out every rigid motion from it. So you have to define a reference condition. Can make use of another picture here. Oops, no. And it's this one. So, again, here you have a slider. Okay, it's a body composed of just 2 elements in this case. In particular, we have 3 nodes, 2 at the extremals of the body and 1 in the middle. Okay. Then there is, as you can see, an element frame for each one of them. Okay. In particular, here you have 6 nodal coordinates, and then there is a body frame B1, I add b into I. In this case, we are in 2D, so b3 is not there. Now, the idea is, okay, this will slide, whatever, so it can slide. How does the body frame has to follow the body while it's rigidly moving? How? Well, again, and eventually, when it deforms, because it can deform, how actually should I impose that the body frame follows, the rigid motion of the body, so that I can disentangle deformation and rigid motion? That's the point, okay? That's the overall question. Well, here, what I do is the following. I impose that the origin, that the direction of B11, so these conditions are arbitrary. So one is as valid as another as long as you are able to take out the rigid part of the motion from the deformation. So one choice of possible is that you enforce that the direction of B11 stay always along the direction defined by the segment going from A to B. Okay, this is the first thing. And since this is a Cartesian frame, if you lock direction 1, you automatically lock direction 2, of course. Then the second, condition that you can enforce is that the origin of the body frame always stays in the middle of this segment AB. If you do so, you will basically enforce that there is no rigid motion possible anymore between the body frame and the body itself. But please note carefully that you see, in this case, there is no attachment anymore, direct attachment anymore between the body frame and the body. So, initially, in this case, the origin of the body, it's actually located on the body. Here, as a consequence of a deformation, it's not anymore on the body. So you see, you lose this attachment, which is so apparent in the case of rigid motion. Okay. And this is why you call this body frame floating frame. Okay. That's why you call it floating frame formulation, because you do not describe motion directly with respect to the inertial frame, as in the absolute nodal formulation. You describe it passing through the body frame, a body frame which floats over the body, so that it takes out the rigid part of the motion itself. Okay. All right. Let's see. So, again, the description of the body is the following. You have a slider body of 6, let's say 3 nodes, sorry, into this space. Okay. And you have to basically take out rigid motion between B1, B2, and the body. Okay. So, oops. How do you actually do it? Let's say that we do what I have just described, but in a mathematically consistent way. Okay. So first of all, let's say the following. The choice of reference conditions is arbitrary. Again, why is it arbitrary? Because it's not more unique, the relationship between the body frame and the body. So you have to choose one. Since it's not unique anymore, you have to choose one among many. And since you have to choose one among many, this choice is arbitrary. Okay, it becomes arbitrary. Okay. We define the following. Okay. We say that QEI, the vector of nodal coordinates of the overall body, can be, in fact, divided into two parts. The first part, which we can call Q0, I, and another part, which we can call QI F0. And then we'll see why F0. So this part, what is it? Is the value of the nodal coordinates before deformation. In particular, this is something that you can associate to the concept of, if you recall, R over bar 0. Okay. So as we disentangle position and displacement induced by deformation in the continuum body description, here we disentangle the nodal coordinates between the one associated to displacement, because you know, as long as you rigidly move it, you will have this. And then there are others associated to rigid move, to deformation. So initial value of if you want, nodal coordinates in undeformed state. Yeah? In the undeformed configuration. And please be aware that these are not a function of time. Okay? So again, this is a function of time. This is not a function of time. This is a function of time. So these Q0i, they are not related in any way to rigid motion. Okay? It's just, you know, the initial position or coordinate of a point, of a node, with respect to the body frame before deformation occurs. Okay? The initial value. This is nodal coordinates induced by deformation. Okay. Then we define the matrix B to I, and please note that I, not ij, okay, as B1. Why? This is actually really how a code works. Huh? It works like this. so that qf0 I, so the vector of nodal coordinates induced by deformation, is equal to b 2, sorry, I applied over q f I of time. And one can say, okay, but I mean, how this is related to the fact that I have to impose a reference condition? All right, we'll see that. In our case, so again, sorry, before actually saying that, this is the vector of nodal coordinates induced by deformation, admissible deformation, okay? Vector of nodal coordinates by admissible, and it will be clear right now. And let's stress out admissible. And if this was m times 1, this is typically, I don't know, we can call it k times 1, and this is an n m times k with k typically smaller than m. So if this is, again, it's a down selection. Let's see this relationship in our case, and everything will become clear, I promise. So in our case, QE I is, we have said, Q0 I plus B2 I applied over this QF I. Now, let's actually see what are the different vectors. Q0 is the initial value of these coordinates. Let's actually report it here, because it's, otherwise we have to go back and forth every time. So allow me to reuse the image here. Okay, so what is the initial? Again, we have to define all these values, these vectors here, to enforce the reference condition that we have said, so that the origin of the frame is such that B1 is always a line between 1 and A and B, and the origin is at the midpoint. Okay, so if this is the case, so in case A, we have the condition 0. So this is condition 0. It's condition here. So what is the value of these coordinates? 1, 2, 3, 4, 5, and 6. Well, I would say it's, if this is if the length is L as usual, so that this is basically L. So we're gonna have, it's minus L divided by 2. Then we have everything is basically 0 until the last, the one before the last one. Okay, so it's 0, 2, 3, 4, L divided by 2, 0. Okay? All right. Then here we will have a matrix B. So this is, again, it's a 6 by 1. Here we have a 6 times, we will see what. And then we have QF, so the vector of admissible of the coordinates used by admissible deformation. So what do I mean by admissible? So in this case, again, we can assimilate the physics, the behavior of this body to what? To a simply supported beam. Okay, so it means that the coordinate QE2 vertical here and vertical here must be 0, null. So it's not admissible to have a non-zero value of this coordinate. Okay, so I do it. I mean, all the rest instead, in fact, are admissible. So this one, Q1, Q5, and the two coordinates at the midpoint, they can all be different from 0 eventually, no? But all the rest, no. Keep in mind that these variables are expressed with respect to the local frame, to the body frame. Huh? They do not encompass any translation, rigid translation of the slider. Okay. So here I have, for example, in our case, QF1, QF2, QF4, and QF1, QF3, QF4, and QF5 for the body number I. Okay. So, for you to be clear, what we are basically assuming is that this is possible, this is possible, this is possible, and this is possible. So, in this case, 1 and 5 basically are axial deformation. No, the body this body can elongate and compress. While instead QE2 and QE6 are transverse displacement, meaning that you can have a bending, and also QE4 and QE3. But 2 and 6 are not possible because it's a simply supported condition. So basically, what you are left with these 4 out of 6. So here we can eventually encircle this just to clarify what they are. And here we have 6 times 4, and this is a 4 times 1. What I'm saying is that when you select these local frame, these element frame, sorry, these nodal coordinates, when you select them, you automatically select where the body frame is. If you tell what they are, you automatically define where and how the body frame follows the body. Okay, and this is what you do. And this means actually eventually enforcing a reference condition. Okay. So, 1. Can node 1 here move along the horizontal way? Yes. So, I would put 0, 1, and 1, 0, 0, and 0. Okay. So you start from minus L divided by 2, and then you can move horizontally. Okay. Then the second node, it has to be taken into account in its variation? No, because it cannot move vertically. So 0, 0, 0, 0. Then the nodal coordinate number 3. It's initially at 0, you see, because it's a midpoint. We saying that the initial value of 3 is 0 and of QE4 is 0, you actually enforce that your body frame has always its origin at the midpoint, you see. Okay, and so you have to take, you know, the effect possible of deformation. It is admissible, so you have to go 1, 0, 1, 0, 0. The same goes for 4. And then 5. Same point, the same that happens in node 1 has to go also for node 3. So you start at L divided by 2, but then you can also move horizontally. So you have to take into account the variation induced by deformation. And so you go from 0, 0, 0, 1. Transversally, there is no combination possible. 0, 0, 0, 0. Okay. In fact, this becomes, if you write it, you know, concisely, then you have 0. Then you have QF3I, QF4I, L divided by 2 plus QF5I, and 0. You see, this is exactly the behavior of a simply supported beam in which the local frame, the body frame, is located always at the midpoint of the line linking point A and B, and with the first direction B1 always aligned towards from A to B. Okay. So it's a concept which really seems to be very complex, but eventually can only be enforced like this. See, and this is, as you can imagine, you know, it's the bread and butter of PC, of computers. You know, this kind of matrices with 1 and 0s. Okay. This is called the reference matrix. And please note that while we have as many connectivity matrices as many elements we have, the reference matrix is only one for each body. Okay. All right. So if you want to sum up, we have that Rij is equal to C2 Ij C Ij C1 Ij B1 Ij applied to Q0 I plus B2 I QF I. Okay. Or, in a more compact way, N Ij applied over Q0 I plus B2 I QF I. Okay, so you see, we were able again to describe the position of each point within an element with respect to the body frame as the sum of two contributions, the initial contribution, the initial value of the coordinates before deformation, and the one directly associated to deformation. This basically unlocks. This is exactly what we needed. Why? Because now we are in the body frame. So it means that the position of a point within the element J of the body I expressed with respect to the inertial frame is what? Is Ri, the position of the origin of the body frame, plus the rotation matrix applied over Ri J. Okay, over bar. And therefore, again, there you go. So this is the exact definition, if you want, of the floating frame formulation, which allows us to pass from the nodal coordinates expressed with respect to the local frame directly to the position of a point of that element, because you see here I still have Pij, because it's the position of a point of the element J within body I, but this time described with respect to the inertial frame. And this I can make use of to elaborate my dynamics equation, because the equation of the dynamics we always write in the inertial frame. Okay. I think that we still have some minutes, and we can elaborate a little bit further on this, but just you know, to describe what we will do next. So once we have this, you can imagine that the next chapter, if you want, the next section of our work will be to use this to build what? We will build, again, the velocity. We will extract the kinetic energy, and from the kinetic energy, we will be able to derive the mass matrix of the element, And please note that here, again, you have the dependence of the position on the vector of nodal coordinates of the overall body, meaning, and this we will stress out tomorrow, that when you will have your mass matrix will be expressed in terms of the nodal coordinates of the overall body. And this is a very important aspect, because, as we will see, eventually you will have to also assemble the mass matrices of each element to form the mass matrix of the overall body. And this will be able to be done, we will be able to do it just to a series, just to a summation. A sum, sorry. Very simple operation. Okay. The last thing that I wanted for you to note is the following, that the presence of the intermediate frame, it's all embedded in here, in this N matrix. Okay. We don't see it in anywhere else. Okay. But it was key for the derivation of our formulation. Without that, we couldn't not derive the overall formulation. And again, in here, in N, lies embedded the limiting hypothesis of small deformation-induced rotations for the elements. Okay. Okay. So this is all for today. Unless there are other questions from home as well, I will stop the recording here.